Good afternoon, everyone. Thank you for being here with us in the Gale Conference. My name is Erin Owens. I'll be the moderator for this lightning talk session. Just a few reminders. We will be adhering to a code of conduct during this conference. I'm putting a link in the chat to that code. If you have any problems related to conduct, please report them to the email address there in the chat. We will be holding questions until the end. If you have a question at any point during the session, please put it in the chat box or the Q&A box. The session is being recorded. You can enable captions by clicking the Show Captions button at the bottom of the screen. So we have 3 talks in this lightning session. I will introduce the presenters as we go through each one. First, it's my pleasure to introduce Elaine Yeung, Doug Dechow, and Jana Remy, all from Chapman University, who will present Unlocking Hidden Insights, Language Classification, and Topic Modeling with BERTopic for academic libraries and librarians.
I'm Elaine Yeung. I'm the STEM librarian.
Good afternoon. I'm Doug Dechow. I'm the Assistant Dean for Research and Data Services at Chapman University.
And I'm Jana Remy. I'm Assistant Vice President of Educational Technology, and I also teach Disability History and Digital Humanities at Chapman University. All right, with that, we're going to go ahead and get started. So Dr. Dechow and Dr. Yeung and I took a workshop, a text mining workshop together last year. And as part of that workshop, we identified a research project that we wanted to carry out. And based on some of our common interests. And what we decided was to do a project that could identify some of the trends and contributions in the field of disability studies from 1900 to 2024 through text analyses. We thought that doing so would allow us to identify key topics, types of journals publishing the articles, and really looking at whether the narratives in disability studies were changing over time. And so as a next slide, Elaine. As a little bit of background, if you're not familiar with disability studies, it's an emerging interdisciplinary field that is really looking at the experience of disabled folks from a social and cultural lens, not so much the medical model that has been typical in a lot of the academic literature around the experience of disabled people. So we wanted to take that and also use the approach of text mining, which allows us to analyze large swaths of text-based data to be able to see trends in the field of disability studies. And what it really allows us to do is to examine way more content that we could humanly read and to track trends within that. I think it's important. I want to note that we chose this specific topic for our project, but libraries are using text mining for a lot of different reasons. And so you might want to consider how you could apply what we're going to discuss for a project of your own that's relevant to your library. So we honed in on the tool of topic modeling to process our documents. And what topic modeling does is it allows or it facilitates the grouping of words that co-occur often in the articles, and it creates topics out of those words. There's different ways to kind of tweak the topics that emerge, but essentially it allows those topics to bubble up. So instead of reading each article and identifying the topic individually, you can do that in aggregate. The best example I know of that I've shared with many folks about what the power of topic modeling is an example from a scholar named Cameron Blevins. We have a link to this in our resources at the end of our talk, who did a topic modeling analysis of a diary of a midwife in early America. It was a 27-year run of diary entries. And he did topic modeling of those to see how the topics in her diary changed over time. Another scholar who did a more traditional work or analysis of those diaries took over 4 years to code and develop the topics, but Cameron was able to do it in a matter of a few days, and their output was really comparable, very similar to each other. And so I think that shows the kind of efficiencies that can emerge from using a tool like topic modeling. But I want to stress that topic modeling doesn't replace domain knowledge expertise. That expertise goes into analyzing and developing that set of topics that emerge from the documents. And so it's still critical to have that in any topic modeling project.
So traditionally, natural language processing or NLP tasks have relied on specialized libraries or toolkits to analyze these large bodies of text that we're talking about. Some of the libraries for doing that are listed here. One of the challenges of using these tools is that different types of NLP tasks, for example, named entity recognition, where you analyze the documents and identify specific words as persons, organizations, locations, so on, or maybe sentiment analysis, where you use NLP to determine the emotional tone of a text. Often these tasks resulted in very different kinds of workflows. In addition, at their heart, most of these tools simply rely on counting the number of occurrences of a specific word and then making judgments as to classify or categorize that word. Large language models change the nature of this process, in part by developing a richer understanding of the context of the words in an individual document or in a large body of documents. Next slide, please. If you've attended a generative AI workshop in the last couple of years, particularly one that spent any time discussing transformers, you may have seen the image on the left hand of the side of the slide. It's kind of box diagram with all the high-level components of a transformer-based neural network identified. And you likely also know that the T in GPT of ChatGPT stands for transformer. Computer scientists love their acronyms, and the BERT in BERTopic stands for bidirectional encoder representations from transformers. The important part in that mouthful is the transformers part. So like GPT, BERT is also a transformer, but that's kind of where the similarity ends. And remember, we're using a BERT-based language model, BERTopic. The full transformer architecture is made up of an encoder and a decoder. So it turns out that both GPT and BERT only implement half of the transformer model, and these halves have specific strengths in the context of NLP. GPT is a transformer decoder, and they are trained to predict the next word in a sequence. And so thus GPT excels at generating text. BERT, on the other hand, looks at lengthy sequences of text from the left and the right, and it's trained to predict a word in the middle of that sequence. So by being trained in this way, BERT excels at understanding text. Elaine?
So for our topic modeling method, we used an unsupervised method, BERTopic, which allows us to explore unknown topics in a collection of text without having to have predefined topic labels. It uses TF-IDF, which stands for term frequency inverse document frequency. So in these basic equations here, you can see how the text is transformed into a numerical vector. So first off, it'll calculate how often a word will appear in a single document. So this TF number of times the word appears in a document divided by the total number of words in that particular document. And then it will measure how unique a word is across all the documents. So it's log of the total number of documents divided by the number of documents containing the word. So each word is given a score, which serves as an input for the learning model. This is the brief overview of our project pipeline. So first off, we'll obtain the data set using a consulate data set builder, which I'll show you in the next slide of a search strategy. We'll read in the JSON line files into Python. We'll do a bit of text pre-processing before using BERTopic to perform all topic classifications. And then we'll generate visualizations. So here are some examples of visual insights that we have generated from using BERTopic. The one on the top is an intertopic distance map, which shows how distinct or overlapping topics are with each other. And then the bottom visual shows the evolution and popularity of topics over a year of publication period. So here we can see trends over time. So we obtained our data set using the Consulate platform, the dataset builder. We used the specific search strategy using the key terms, disability studies, and intellectual origins or history or evolution. So we chose to have limited our results to only articles from the JSTOR provider from the year 1900 to 2024. So we obtained about 3,800 full text articles, and we requested a customized data set that includes both the abstract and the full text.
So let's talk a little bit about the actual implementation of what we did here. If we haven't set up to this point, BERTopic is a Python-based library. So you may need to have some Python programming skills, but with the assistance, ironically, of ChatGPT, maybe not as much as you might think. Unfortunately, BERTopic's not available for R. So what we have here, what we see on this page, very much adheres to the items that were listed on the project pipeline slide that we showed a little ago. At the top level, we're going to make sure that BERTopic and all the other necessary libraries are available to the Python script. We need to load our data, the files or corpus that we want to analyze. We need to create an instance of the BERTopic model, and then we need to fit that model. I can say a little bit about that in a second. And then we're going to visualize the results in a number of ways. Before we break down the code any further, one of the important libraries that we've used in this project is Pandas. If you haven't used it before, you can kind of think of Pandas data as a big spreadsheet, rows and columns of data that are available to your Python program. And the Pandas data frame format is one of the data formats that BERTopic can work with. Right after that, we see the creation in the code of the BERTopic model. That's step number 3. This model handles all the technical details of the topic modeling process. It's going to embed the documents, cluster the results, develop the documents, the topics from the documents. Crucially for this step, you have to provide a specific language model. Here we used a language model named All Mini LM L6v2. It's available from Hugging Face. There are a number of libraries there that that will do the same thing. Crucially, this one is an SBERT or sentence BERT model that is designed to understand sentence level language. And then next we fit the model. Fitting, if you haven't heard of it before, is the process of exposing the model to new data, our documents, so that it can make predictions, the topics, about this specific data. And then next is the visualization process. And I'm going to let my colleague Elaine say a bit more of that as she shows you some of our results.
So even though for our particular project, we looked at a corpus of disability studies literature, it's a flexible tool and that we can also apply to a range of qualitative text data. So we used BERTopic on a library instruction feedback survey from first-year undergraduate students, where they were asked in an open-ended response, what do students find most useful about the library instruction sessions? And these are the visualizations we gained from BERTopic. So on the graph on the right, it shows the topic word scores. These are the top keywords that students have responded to in the feedback survey. And within each topic, it shows the top keywords for how frequently students mention them. So you can see that students valued learning about sources, search, looking for books and articles, and in topic 5, the SIF evaluation method for article reliability. And on the left here is a similarity matrix, which shows how closely related different topics are to each other. The higher the more darker the box, the more closely correlated the topics are with each other. So you can see for topic 2, library resource, it is in the dark blue in comparison with topic 16 on the bottom with the library website. So student value learning about library resources, in particular navigating the library website, which you can also see in topic 7 and in topic 12 using the library search engine. So with this data, we can enhance our data-driven decision making. We can improve our library offerings by based on these feedback evaluations. We have analyzed this feedback, which will further support improvement of our teaching assessments for the next academic year. So using BERTopic can be a very powerful tool for analyzing data. And if you have more questions about BERTopic and topic modeling, there is a link to this PowerPoint in the session description. You can find more readings here. And if you have further questions after the Q&A, you're also free to contact us by email. And lastly, we give our appreciation to Ithaca's consulate team with saddened by the sunsetting, but it has been a great resource for our text mining learning.
Thank you.
All right, thank you so much. That was wonderful. I'm going to introduce our second talk. Researcher librarian Jeremy Kenyon and JournalMap founder Dr. Jason W. Carl will present JournalMap, a method for using AI to enable improved geographic indexing.
Can everybody see and hear that okay?
Yes, indeed.
Okay, thank you very much. Now, my apologies ahead of time. I have a marching band literally outside my office, so hopefully the marching band sound doesn't come in too much into our talk here, but we'll see. So thank you for having me. My name is Jeremy Kenyon. I'm a research librarian at the University of Idaho. My colleague, Jason Carl, couldn't be with us today, but we're here to talk a little bit about a project that we've been working on called JournalMap. JournalMap was an IMLS funded project until 2026. So unfortunately, it is not a project any longer, but at least not a funded project any longer, but we'll keep going. And I'll talk to you a little bit about some of the ways that we're looking at using AI in our project. So I'm first going to start with a little bit of a presentation of what JournalMap is. Talk a little bit about the problem that we're trying to deal with in terms of the discovery of literature. Specifically the problem of geoparsing, which is the issue that we have, and how we can use generative AI possibly as a solution to that. So we have some results from some studies that we've done, and we'll talk a little bit about that and then where we're going as well. JournalMap can be found at this website, journalmap.org, hosted by the University of Idaho behind the scenes. It's a pretty straightforward service. It is a tool for discovering literature based on geography. So you certainly can search using any kind of standard article metadata that you would normally search, but you can also use the map interface to look around and find things based on geography. You can kind of see that in the picture here. We also introduced the capacity to browse by what we call locational attributes, or the biophysical attributes of a given location on the Earth. So it's not just, look around the map and find things, but you can also filter by biome, by elevation, by precipitation. We've introduced socioeconomic data sets like population density. And so if you're looking for studies on soil erosion, you can look for places on the Earth that have similar environmental characteristics in order to do that. It's a non-custodial system, so we're basically processing articles, and then we're not keeping the content itself. We're just keeping the metadata, and so in that way, we're hopefully sort of getting around some of the issues of maintaining any kind of long-term record of a lot of copyrighted material. We just need to process it once, essentially. We have an API that allows us to use this not just as a website that you can go to and search around on, but also as a service. So if you are interested in getting a bunch of literature indexed by its location and its attributes, you can submit those using the bidirectional API. There is some permission process that you have to go through to do that. But you can also get content from that. So you can reuse it somewhere else on some other project or some other service any way you want to. So our goal with this project was not to have anybody completely limited to using our interface, but rather to create a service that allows others to reuse content in creative and new ways. This is the workflow for JournalMap, and I'm not going to go through this whole thing, but I will point out the yellow box right in the center, and that is where we focused on our automated geotagging process. And up to this point, we've used tools that are not kind of the generative AI large language models that you typically see. We've been using some older tools for doing that, but we're probably going to be transitioning soon to using generative AI based on the results that we found, which I'll talk about in a second. Of course, any process where you automate the creation of metadata from some set of algorithms or tools, you need ways to fix those cases where you have errors. And so we have mechanisms built into our interface to be able to edit geometries and correct them when the AI tools are incorrect about their conclusions. I I want to step back just for a second and talk a little bit about what we're trying to do. The point of JournalMap and tools like it is to, help you find out when things that are unexpectedly similar are similar. And so my colleague, Jason, kind of created this idea when he was working out of New Mexico. You see the landscape there on the left. And then he traveled to Windhoek, Namibia, and he found that, the soil was very similar, the aridity levels were very similar, some of the vegetation and the way it interacts was very similar. And so you may not have realized that being able to do a study in one place would have import for the other place. And the ability for anybody to know all the different places in the world that possess those same characteristics is pretty unlikely. And so creating some kind of tool that allows us to do this is beneficial. Traditionally, when we've indexed or classified literature in terms of its geography, we've used something sort of like what you see on the right, which is a list of keyword terms or subject headings. Somebody laboriously went through the process of saying, what kind of place is this? What kind of terms are important here? What's the aboutness of this in terms of geography? And that, in all honesty, is partially the limitation as well, that we have a significant focus on the what of science, but not very much on the where of science. And so we're trying to improve that with JournalMap. Of course, the English language, particularly when it comes to geography, can be really complex and difficult to parse. The little example that you see here shows on the left in box A, all the studies that reference the Chihuahuan Desert. So if you did a keyword search looking for those studies, you got all these different places, and that's all the different locations where those studies were done. On the right, you see the little box that shows the actual Chihuahuan Desert and the studies that actually did take place there. So if you're trying to find B, it's really hard to do it using traditional search methods that you see over on box A. Once, of course, you have a location identified, it's relatively straightforward to generate all those attributes. We can use traditional geospatial processing processes to do that against different kinds of data sets. However, generative AI introduces some possibilities there as well, which I'll talk about in a second. So the actual technical problem that we're trying to deal with requires kind of two components. The first is processing the language or text of a document, and then identifying the study location of that paper. Not all studies have locations, but many do. And then once we've identified that location, it's coming up with a location on the Earth, so geocoding that. And typically, we would use tools very much like what you heard about in the previous presentation, named entity recognition tools like Spacey and others. For geocoding, there's plenty of tools out there as well. GeoNames is one of the most common gazetteers on the web, but Esri and Google have geocoding services as well that you can use. And so when you're parsing the text itself, you typically have two different kinds of components. You have structured text coordinates. Those are pretty straightforward to work with. But you also then have unstructured text. And, we use place names in so many different ways. Here's a bunch of examples of them that you see. They're really tricky to figure out when is a place name actually referring to a place and when is a place name used in some other kind of context. Fortunately, AI models have gotten pretty good at determining context. To demonstrate the problem a little more specifically, you can see this text here. We use Spacey on this, and our goal is to identify what you see in the orange and yellow boxes in the center of the picture here. We want to identify the phrase Parker Mountain, Utah, USA as the site of that study, and the rest of it, for this purpose at least, we're not that interested in. Once we identify that location, then we'll use something like GeoNames, which is what you see here, to identify those coordinates. And to do that in a semi-automated fashion is the goal. So a couple of years ago, we evaluated, as we were starting this process, a number of different tools for doing this processing. And again, this is all kind of right before the big explosion of GPT and other tools. So we found that there's actually a tool called Mordecai, which was a DARPA project focused on being able to identify a geographic location based on unstructured text. That worked best at about 65% of the test articles that we used. We had 120 articles. with about 143 locations. Some studies have multiple locations. And Mordecai was the best of those. You'll see a number of those other tools are less performant in trying to solve this particular problem. But of course, the large language model explosion happened. All these tools came out, and so we decided to kind of pivot to seeing how well those tools could do at, identifying a study location and then possibly even geocoding if possible. So we looked at 3 different LLM tools: GPT 3.5, Bard, now been replaced with Gemini, and Claude 2, which again you'll notice is a little outdated. And then, of course, because these are generative AI tools, one of the questions is, if you run this again and again, are you going to get different results? So we also looked at repeatability in this study. And what we found is, if you'll remember, Mordecai, our current sort of best-in-class tool, performed at 65%. Gemini, ChatGPT, Claude all performed better than that, more or less. And Claude itself, this was Claude 2, not even Claude 4 that we have today, performed a lot better. And then in many cases, it was able to generate coordinates for those studies as well, and in some cases, pretty precisely. And so using fairly simple prompts, we were able to get pretty consistent and high quality results. Not, I would say with the exception of Claude, the other two are probably not quite performing at human levels, but Claude is doing a pretty good job in this particular study. Then we went ahead and ran those tests 10 times on each of those tools to see what kinds of different results we were getting in each case. And you'll notice that more or less, they all sort of end up with a pretty good result. And again, Claude ends up being the best. The box down in the left, you'll notice the variability of those locations. So depending on the precision that we're interested in, that may or may not be an issue, but they're all pretty much in the same area, more or less. Down in the bottom right, you'll see Bard, now Gemini's, occasionally really ridiculous results where they get things confused and they put it on the other side of the world, and those kinds of results aren't too useful for us. Of course, those tools are a little bit older, so there's some newer models that are out there. Here's an example on the left. You'll see this study that is in Hawaii. GPT 3.5 couldn't give us coordinates, but by the time 4.0 was released, we were able to get those coordinates, and those are accurate coordinates for that location. More recently, we thought, well, if it can do the LLM, or if it can do the location extraction from the article, what other kinds of things can we get out of the latent knowledge that's built up in some of these tools? And so we decided to go ahead and try generating attributes as well. And by and large, it does a pretty good job. It can give us some estimates on elevation, biome, slope, precipitation levels. Now, here's the issue. I think everybody here is aware of the hallucination problem. And so I think at this stage, we're not willing to rely on LLMs for attribute generation, but building in this kind of testing will allow us to pursue this maybe in the future. So where are we headed in the future? We're going to go ahead and implement those LLM tools for geolocation. We're going to start testing and exploring what we can do with attribute generation, but the potential with AI tools is pretty significant for generating this in an efficient and fast way. We're going to index more content because it gets better as we have more stuff in it. And then we'll probably expand to other kinds of things as well, including temporal dimensions. And so, again, this is a project that lasted a couple of years. We have partners at Kansas State and the University of Arizona, lots of librarians on this. And so my thanks to everybody who was involved, and happy to answer questions a little bit later if you have any. And thank you for your time.
Thank you so much, Jeremy. All right, and I'm going to introduce our final presenter, Cindy. I'm sorry, Cindy, I forgot to ask you how to pronounce your last name, so I apologize.
Cindy Tian.
Cindy Tian, the metadata librarian at the University of Notre Dame Law Library, will present AI-powered metadata, a foray into cataloging a born digital collection.
Thank you. Can you see and hear me okay?
Yes, indeed.
All right, thank you. I am glad to share a case study today on how we explore the practical use of generative AI to streamline metadata creation and extraction for a born digital collection. Before diving in, just a quick disclaimer that I'm using the term cataloging here in a broader sense. The metadata in this project was structured specifically for an institutional repository following the Dublin Core schema, not traditional MARC cataloging standards. In this lightning talk, I'll give a quick overview of the collection, walk through the workflow we developed, and share a few reflections on the benefits and limitations of using AI for library metadata work. Born digital collections are defined as content produced in digital format rather than digitized from physical sources. A 2022 study identified 3 major obstacles that affect the discoverability of born digital collections, and that is data protection, scale, and skill gaps. The study noted that smaller institutions in particular often struggle to catalog large volumes of data due to limited staffing and financial resources. As a relatively small library, we resonate with that statement. One example is our work on a special collection, the Indiana Continuing Legal Education Forum, or ICLEF. This collection includes materials from annual legal seminars hosted by ICLEF. Since 2020, these materials have been published in electronic format only, like many resources today, making them more born digital. In 2023, during our library's ILS migration, we started housing this collection in our institutional repository, which runs on Digital Commons or BPress. We've made it a special collection that we continue to update as new materials come in each year. The materials are delivered to us in PDF format, organized into numerous folders. And each folder, named after a specific event or seminar, represents a session held on particular dates within the year. There are typically around 100 folders in each annual batch. Now, if you were a cataloger and looked at about 100 folders with PDF files, you would probably wonder, how am I going to catalog all of this without any metadata that was provided to me? Well, that was me these past couple of years. And to put this collection into the Remy model that is used to describe bibliographic entities, and that is work, expression, manifestation, and item, each one of these folders can be considered as a separate manifestation that requires its own metadata record. So the process of extracting and creating metadata essentially mirrors original cataloging for each title. The key metadata elements we needed include title, abstract, keyword, and full text URL. All the steps were originally done manually before I experimented with AI. And as you can imagine, with the sheer volume of files, the process was quite labor intensive. To address these challenges, I experimented with 2 Gen AI tools, ChatGPT 4.0 and Gemini 2.0. I chose these tools based on their availability and ease of use. ChatGPT 4.0 is a paid model, currently at $20 per month, and Gemini was recommended by my university's generative AI task force for campus-wide use, especially in cases where data privacy and security are important concerns. As you can see here, the folder names follow a consistent event name-event date pattern. This is the building block for our title and abstract extraction. We use the event name as the title and then formulated a standardized abstract based on the date. I tested Gemini by providing a screenshot of the folder names along with this prompt using natural language, just describing what I needed to be done. And I provided example here to make sure my request was clear. As you can see in the screenshot, Gemini successfully processed the image, likely using optical character recognition or OCR, and accurately separated the information into 2 clean columns. The before dash column, i.e. the event names, are the titles we needed. For the abstract, we used a simple text template, meeting proceedings of a seminar by the same name held on a particular date. So the key task here was to take the extracted date, i.e. the information in the after dash column and plug it into that sentence for each title. And my prompt was this. The p tags in the bracket were required by the metadata schema, so I included them in the prompt for easy copy and pasting. As shown here, Gemini added the abstract column in the requested format. So after 2 prompts with 1 screenshot of the folder names provided, the titles and abstracts were then quickly and accurately extracted and formulated, which really helped simplify our workflow. Plus, it provided the option to export the table into Excel, making the next steps of processing more efficient. For keywords, we use controlled vocabulary from the Library of Congress subject headings, or LCSH. This process had 2 parts. For recurrent seminars, we reuse the same keywords as previous years to maintain consistency and support cross-repository indexing. For new seminars with no prior instances, we assign new LCSH terms. This is the prompt I used where I provided ChatGPT 4.0 with a list of the 2024 titles, along with the 2023 titles and their corresponding keywords. Again, I provided an example in the prompt to make sure my request was clear. And ChatGPT 4.0 responded by identifying fuzzy matching as the best approach for comparing similar but non-identical text strings. It then generated a table that matched up similar titles across the 2 years data sets and assigned the corresponding keywords. And that sounds pretty great, right? Well, except not entirely. After reviewing the results, and apologize for the fuzzy image here, I noticed quite a few mismatched titles. The green highlights correct matches and the yellow marks the errors. For example, it matched the 36th annual Medicaid in Indiana for the elderly and disabled with the 2023, the ethics triangle. Clearly not the same seminar, resulting in completely irrelevant keyword assignments. After going through the entire spreadsheet, I found that the correct match rate from ChatGPT 4.0 was about 41%. And to cross-check, I ran the same dataset and prompt through Gemini, and its match rate came about 31%. I ended up having to manually map the rest of the keywords. So on the bright side, AI did save me time for that 41% that were accurate. But overall, the results really underscore the current limitations of Gen AI, especially when it comes to nuanced or domain-specific matching, and highlight the continued need for human oversight and correction of its output. Finally, the full text URLs are generated after uploading the PDF files to the backend of our repository content management system. Digital Commons supports batch uploading, which is great, but there's a catch. Since each PDF file is nested inside its own folder, we first needed to consolidate all the files into a single directory to enable batch upload. Rather than manually dragging and dropping hundreds of files, I turned to ChatGPT for help automating the process. It offered a few solutions, including using command line tools or a Python script. I went with the Python option, and for someone like me with very limited coding experience, it turned out to be quite manageable. All I had to do was copy the script, update the source directory and destination directory paths, and run it. The script worked as intended. It successfully located all the files within the folders and copied them into a single destination folder. And this small automation step significantly reduced manual effort, allowing us to batch upload the files and generate the corresponding URLs all in one go. So, as we've seen, using Gen AI tools in this project helped improve the efficiency of metadata extraction and creation for a born digital collection. I do want to acknowledge that many of these tasks could likely have been automated by experienced programmers without the help of AI. But for people like me who don't have a deep background in coding, AI really helped bridge that skill gap and enabled me to automate tasks that would otherwise have been too technical or too time-consuming to take on alone. And circling back to the study I mentioned at the beginning about how smaller institutions with limited staff and resources often struggle to catalog large volumes of data, this kind of tools can be especially valuable. The time saved here might open the door to projects that would otherwise be out of reach. It also helped us streamline future workflows and gain hands-on experience with AI for metadata tasks. That's particularly important at a time when many libraries are navigating shrinking budgets and reduced staffing. And in that context, learning how to work smarter with the resources we do have becomes even more essential. And that brings us to a few final reflection points. While AI tools have shown some impressive potential, as this case study has demonstrated, they also come with real limitations and risks. One major challenge is hallucination, where AI generates incorrect or even fabricated information. In my keyword mapping experiment, for example, both tools produced a number of mismatches. And unlike traditional programming, large language models like ChatGPT operate more like black boxes. You private input, you get output, but the process in between isn't fully transparent. And that means we can't always predict or trust AI responses without scrutiny. Critical thinking remains essential. And of course, critical thinking has always been central to cataloging and metadata work. Catalogers are trained to analyze, evaluate, and make informed decisions about how to describe resources. And AI doesn't replace that skill, it amplifies it. In fact, I think we should approach AI as a capable assistant, not as the decision maker. And in that sense, perhaps the future of Gen AI, at least in the metadata and cataloging field, lies in AI assistant rather than fully AI-generated metadata. There's also the matter of privacy. Many Gen AI tools retain or reuse input data to train future models, so it's important to be mindful of what information you're feeding into them. In my case, the dataset was open access, so there were no concerns or restrictions. But for institutions dealing with sensitive or proprietary data, it's crucial to evaluate privacy risks before integrating AI into workflows. And another important ethical consideration is the environmental impact of AI, which has been discussed in some other great sessions at this conference. Studies have shown that the computational power required to train and run large language models consumes significant energy and fresh water. While I've mentioned the efficiency gains AI can offer, we also need to reflect on what we mean by efficiency. Are we unintentionally contributing to environmental harm in pursuit of saving time? And these are complex trade-offs, and there may not be easy answers to any of these questions, but that doesn't mean we should ignore them. Responsible use of AI means recognizing both the possibilities and the costs and making informed, intentional decisions about when and how we bring these tools into our work. Thank you.
Right. Thank you so much, Cindy. So we had 3 excellent talks, and now we're going to open the floor up for any questions. Please feel free to add your questions into the Q&A box. If you would prefer to unmute and ask your question, you're welcome to raise your hand, and I can unmute your microphone. Okay, I'm not seeing any questions so far. Well, thank you all so much for sharing your work with us. We had some very insightful ideas shared here. All right, and if we still don't have any questions, we're just about at time, so I will go ahead and wrap this up. Say thank you everyone for attending. Thank you to our presenters, and please enjoy the rest of the Gale conference.